Welcome to another edition of RCE. Again, this is Brock Palen. You can find us online at rce-cast.com, and we're coming up very, very close on episode 100. Once again, I have Jeff Squyres from Cisco Systems and one of the authors of OpenMPI. Jeff, thanks a lot for your time.
Hey, Brock. Yeah, today this is actually fairly timely because the HPC community was just kind of rocked in a little turmoil with that certain little blog post from Mr. Jonathan Dorsey about how HPC is dying and MPI is killing it. And one of the big things that he cited in there as a comparison point was that the big data community seems to be growing much faster than the HPC community. And it's actually just completely coincidental that we're actually interviewing somebody from that community today.
Yeah, so one of the things he referred to was Spark, and Spark's something I've been screwing around with and having a lot of fun with. But one of the things Jonathan pointed out was that you're able to still write. He actually wrote diffusion using Spark in much less space than it takes to use MPI, and he had job postings and other stuff. And so that was really interesting, and I thought a lot of it was because people just don't know these things exist, which is part of the reason you and I do this. And I wrote about that at Failure as a Service, which is my blog, and basically I think people need to learn about these things. So I gave it away. We're talking about Spark today. So let's go right in. Matei, take a moment to introduce yourself.
Hi, thanks for having me on the show. I'm Matei Zaharia. I'm an assistant professor at MIT working in distributed systems, and I started the Spark project while I was a grad student before that, and I also spent the past 2 years commercializing it through this company called Databricks.
So I wonder could you give us the quick rundown? What is Spark? Give us the quick answer, and then we'll dive into more specifics.
Yeah, sure. So Spark is a parallel computing framework for data processing on clusters. It lets you use some concise APIs in Python, Java, or Scala to process data at scale.
So people are probably most familiar with the MapReduce paper, which is actually quite old now, and the big data analytics community really kind of got running when MapReduce kind of got brought to everyone's mind. How is this different than MapReduce?
Yeah, great question. Yeah, so Spark is actually inspired by MapReduce, and it tries to generalize the MapReduce programming model so that you can capture more types of algorithms or of computations, but still keep the nice properties of MapReduce, such as fault tolerance and automatic distribution and placement of computation near the data. So it started, our research group was actually doing research on MapReduce, and as we saw people trying to use it for new applications, we designed this new model.
So Hadoop is known as kind of the front runner in terms of a MapReduce framework that's out there right now. But Hadoop offers a lot of things. Does Spark replace everything about Hadoop?
Yeah, good questions. So Spark does not try to replace everything in Hadoop. The part it replaces, or the part you can use it for, is the distributed processing part, which is what MapReduce would do. But the Hadoop stack also contains a lot of other projects. It contains storage systems such as the Hadoop file system, and Spark can use those, but it's agnostic to those. It doesn't try to provide its own file system or anything like that. And likewise, all the key value stores and things like that are in the Hadoop stack don't get replaced. So Spark is used most often in Hadoop environments alongside the other components of the Hadoop stack.
So what then is the value of Spark? So if I'm using it inside Hadoop, and at least to me, a novice in the big data kind of world, why wouldn't I just use pure Hadoop, all the things that come with Hadoop that allow me to do MapReduce and the like?
Yeah, good question. So the main part is that the Spark execution engine lets you do more types of computation and often faster or more easier to program than you would using MapReduce. So there's kind of two pieces of that. One is that the engine is designed to be highly general, so it can do not not just batch computations like MapReduce, but also streaming computations or interactive queries where you're sitting at a console and typing in queries and getting answers. So basically, it's this wide range of things. And then the APIs for it are quite a bit easier to program with than the MapReduce API. So it's these high-level functional programming-based APIs in Python and Java and Scala, and many of the things that you'd have to write custom MapReduce code for in Hadoop, there's already a library function to do it in Spark. So it's just faster to put together programs.
So does Spark itself utilize any of the MapReduce algorithms, or is it pretty much taken what you saw a lot of people doing with MapReduce and worked with it?
It utilizes some of the ideas that were in the MapReduce architecture or design. So, for example, ideas like sending computations to the nodes that contain the data, and tracking enough about the computation to figure out how to recover from failure. But it doesn't use the code in Hadoop MapReduce. The only part of Hadoop it interacts with is the storage systems, and it can use the same interfaces that everything else in Hadoop uses to read from any Hadoop-supported storage system.
So now when you say that Spark is faster, how does it get that speed up?
Yeah, good question. So there's two main things that contribute. One of them is that Spark lets you control and use distributed memory in your program. So if you have a bunch of machines, you can choose to load data sets into memory across of them, keep them there across queries. And if you have any kind of iterative algorithm or any kind of interactive queries where you're asking multiple queries on the same data set at once, that part is quite a bit faster. In traditional MapReduce, you don't have any control over memory. You can't have like a variable that you load into memory and then you share across MapReduce steps. So this is the first thing. And then the second thing is that the engine also supports more general sort of computation graphs. So if you look at MapReduce, it's just these two phases, map and reduce. And if you have an algorithm that needs to do more phases of communication, for example, you have to run it as separate MapReduce jobs. And there's quite a bit of overhead to starting each job and feeding data from one of them into the next one because it has to go into a file. And with Spark, you can have a more general graph with multiple stages, and this also helps improve performance, even if you're not using the in-memory features at all.
So that's an interesting point you raised right there. One of the big performance criticisms of typical MapReduce / Hadoop and all of its clones is that it has to read and write to files all the time. Mm-hmm. And there are a lot of reasons why it was architected that way. But am I reading between the lines of your answer here that you don't do that, or you don't have to do that in Spark?
Yeah, exactly. Yeah, we can avoid that in a lot of cases. And in particular, in MapReduce, the part that's really slow, really time-consuming is the output of each MapReduce job has to go into a file in a distributed file system. So it actually has to be replicated across nodes for fault tolerance, and it's very expensive to do that right. And then you do that, and then immediately you just read it into another Hadoop job. So in Spark, if you just merge those jobs together into one execution graph, you can avoid all of that.
So Spark tries to do a lot of this stuff in memory, but do I have to do anything special if, say, the data set I'm working with is larger than the piece of memory? Do I kind of have to manually manage this in memory, out of memory?
Yeah, the way it's designed, you don't have to do that. So it will gracefully sort of spill out to use the disk if it can't fit things into memory. Of course, if you want, you can try to manage it. You can try to tell it, well, you loaded a data set and you want to remove it, and so on. But even if the data sets don't fit, the idea is that you shouldn't have to change your program based on the size of the cluster you're running on and how many resources there are. And this is also helpful, actually, if machines fail in the middle of your program, or if your job needs to be resized down because you want to launch another job or stuff like that.
Okay, now that's an interesting point right there too. So what